Students, in this video we'll prove the Cayley-Hamilton theorem. Let's let A be an n by n matrix with complex entries and P of x, PA of x, is characteristic polynomial. Okay, of course, what does that mean? That means that PA of x is just the determinant of A minus x times the identity matrix. You can also put it as just x identity minus A. It doesn't matter. Some books have it a little bit differently, but the same result's going to be true up to a plus minus 1, right? All right, then the Cayley-Hamilton theorem. Cayley-Hamilton states that PA of the matrix A is the zero matrix. Okay? Excellent. Okay, so how do we prove this? So of course there's a long history of this theorem, and let me do a proof in sort of the simple case first, right? And so let's suppose first, so here's a proof under a diagonalization assumption. In other words, if we assume, so let me prove this assuming that the operator A is diagonalizable, right? So if I assume that A is diagonalizable, there's an invertible matrix P, a diagonal matrix D, and an invertible matrix P inverse such that A has this factorization, right? Then it turns out that the characteristic polynomial, then PA A of A, then PA of A is PA of P D P inverse. And we know that this, if I have any polynomial of PD, any power of this, P D P inverse becomes P D to the K P inverse. So this is just P, the polynomial PA of the matrix D, and then P inverse over here, right? And so now, of course, what's going to happen over here is this is just going to be the polynomial applied to the diagonal entries, the eigenvalues. So this is P, and then it's going to be PA of lambda 1, PA of lambda n, because those are the diagonal entries, right? And now, of course, that is just the zero matrix. So when I plug an eigenvalue into the characteristic equation, I get 0. So this is just the zero matrix n by n, right? Zero matrix over there. Okay, so if the matrix is diagonalizable, the argument is very, very simple, right? Now, we know that not every matrix is diagonalizable, so we have to figure out how to generalize this argument, right? And so the natural way that we generalize this is to use the Schur factorization, right? So by Schur's theorem, so that's sort of the easy proof, and this is the proof you want to keep in the back of your mind, right? Because in some sense, there's actually an easier proof of Cayley-Hamilton, which says that you can perturb your matrix a little bit to make it diagonalizable, right? So in other words, this is not sensitive to small perturbations in some sense, right? Using continuity, right? But that brings us into ideas of analysis, and then in a basic linear algebra course, we don't want to use like perturbation arguments from matrices to do this, right? We want to use sort of general factorizations, right? And so now, what's the proof in general? So by Schur's lemma, A is unitarily equivalent to an upper triangular matrix. Unitarily similar.
Not P.
In other words, A is going to be a unitary matrix U, an upper triangular matrix T, and then since it should be unitarily similar, right? So that's going to be U star, right? And so, of course, what's the key over here? So U, then U star is the identity, right? So in other words, that's really U inverse over here, right? So A is equal to U T U inverse, like that, right? And so now, of course, by the same trick as before, this implies that PA of A is really going to be U PA of this upper triangular matrix T, and then U inverse over here, like that, right? And so, of course, since T is upper triangular, we know that the diagonal entries of T are the spectrum of A. So in other words, note that the spectrum of A is the same as the spectrum of T, right? Which is the diagonal entries, right? Just going to be the set of points T11 through T1n, like that. TNN. So the diagonal entries, okay? Excellent. And so now, of course, let's factor A. So what does PA really look like? PA of X where it looks like, up to sign, of course, x minus lambda 1, x minus lambda n. All right, and so now using this argument over here was PA of t. So PA of t is going to be just t minus lambda 1 identity, t minus lambda n identity. Like that. Now, there may be some repeats in here, right? In general, there will be repeats for an arbitrary matrix, so I could have repeated eigenvalues, but the sure factorization, the sure lemma is true in general, right? And so now, let's look at the matrix representation of this T1 over here, right? So T1, lambda 1 minus the identity, has what matrix representation? So T1, T minus lambda 1 identity, has a matrix representation with respect to this U, with respect to the standard basis, right? What's it going to look like? Well, I know that T11 is lambda 1, so this first whole column over here is going to be all zeros, right? And then what's going to happen over here? It's upper triangular, so I don't know. There's something non-zero over here. Let's call it maybe like an A. And then there's going to be a T, then you're going to have a T22, or a lambda 2 minus lambda 1, right? Lambda 2 minus lambda 1. Then all zeros below it. And then some other stuff over here, right? Star, and then star, like that, right? And then let's look at T lambda 2, T minus lambda 2 identity in the standard basis. What's that matrix going to look like? Well, that matrix over here, I'm just going to put it over here, is going to look like what? That matrix representation is going to look like something. Well, it's going to be a lambda 1 minus lambda 2 up here, lambda 1 minus lambda 2, like that. And then what? And then you'll have something over here. Then you're going to have a what? Then you're going to have something over here. Don't know. Called B, like that. Then you'll have a 0 over here, right? Then you'll have a 0 over here. That's the key feature over there now, right? And then zeros below, like that, like so. And so now what happens when you multiply these two factors over here? So let's look at this first one over here. So the first row, if I did first row, first column, it's going to give me a 0. And then if I do first row, second column, that also gives me a 0. Then over here, what we get? We'll get a 0 over here and then a 0 over here. So if I look at this factor of T minus lambda 1 identity and T minus lambda 2 identity, they'll have a 2 by 2 block of zeros up here, right? So hence, T minus lambda 1 identity, T minus lambda 2 identity has a 2 by 2 zero matrix in the slots in the upper left corner. All right, and so now when I have that, when I do that first part of the factorization, so we're going to have over in the next phase of this, we'll have a 0, a 0, a 0, a 0, then something else which we don't know, something else which you don't know, zeros below it. And now what will happen when I do a lambda 3, right? When I put a lambda 3 minus identity, then that's going to give me a 0 in what entry over here? In the 3, 3 entry, I'll get a 0, right? Well, from the 3, 3 entry, I get a 0. When I do this product over here, I'm going to get a 0, a 0, a 0, a 0, and then I got a 3 by 3. So if I do this with the matrix of T minus lambda 3 identity, has a 3 by 3 zero matrix in the upper left corner. Great, because now what does that show me? That shows me over here that when I look at this factorization over here, if I keep doing this over and over and over again, this will have all zeros in the main diagonal, right? This has all zeros in the main diagonal.
To meet.
Right? And that shows with respect to the standard base that if I plug in any of these elements over here, that I'm going to get these blocks that give me 0, 0, 0, 0, 0, 0, 0, 0, 0. So this operator over here, so by doing this over and over and over again, what happened to E1 and E2? E1 and E2, when I plug it into this product, lambda t minus lambda 1 identity, t minus lambda 2 identity, give me a 2 by 2 matrix of zeros, right? So with respect to that basis, I got a 2 by 2, then I got a what? Then I got a 3 by 3 matrix that were all zeros, and I'll get a 4 by 4 or 5 by 5 by proceeding by induction. So by induction, t minus lambda 1 identity, t minus lambda n identity is just going to be the zero matrix, because what's going to happen is I'm going to keep getting a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5, a 6 by 6, a 7 by 7, all the way down to an n by n matrix of all zeros, and that proves that this t, that PA of t is the zero matrix over here. So that proves that what? That proves that P applied to A is equal to 0 is equal to the zero matrix. PA is the zero matrix for an arbitrary matrix over here. For an arbitrary matrix over here, A. So PA of A is equal to the 0 n by n matrix for all matrices A, and that proves the Cayley-Hamilton theorem. Thank you very much.